It is my great pleasure to introduce Yuan from the University of Oregon. So nice to have you here. And he will talk to us about approximation and orthogonal polynomials. Many thanks for being here. And well, please, please start.
Okay, thank you. And it's nice to see everybody. And I'm not sure about the level of the talk, so I'm trying to be make it more like expository. So let me start with first line. Oops. Yeah. So let's just think about approximation and orthogonality from a very general point of view. So consider a Hilbert space. So it essentially has a inner product, and that phi n be an orthogonal base in this Hilbert space. That really just means phi m equals 0 if n is not equal to m, and phi m is bigger than 0. And if that's the case, then every f in H has an expansion, what we usually call the Fourier expansion. So f can be written as an infinite sum, where fn is simply going to be the ratio of inner product f with the base divided by its norm. So the norm of the space just ff dot square root. Then the Fourier series converges if this partial sum equal to 0, where Sn equal to just the sum of this. So this is what we usually teach in calculus and in elementary analysis. So the partial sum SNF is an approximation to F. In fact, it is even more. It's what we call least square approximation. So that means your SNF minus F is the among all sums, finite sum minus F. You take the minimum of all the coefficients, and that's the minimum. So this is clearly the case if we consider the classical Fourier series. Well, classical Fourier series is have the inner product. It says fg 0 to 2 pi, where you take orthogonal base, just cosine sine, cosine sine, cosine 2 theta, sine 2 theta, and da 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 da. That is your orthogonal base. So in this talk, we will work with the setting of the inner product in the following form. It's fg equal to integral over omega, where you have fx gx and wx dx. Well, wx is fixed. We call it a weight function. You can think about this whole thing as a dnu. So it's just fx times g is a integral, where omega is a domain in Rd. So our orthogonal base consists of polynomials. I'm thinking about not trigonometric polynomial, but really the genuine algebraic polynomial. And I'm only consider real, not complex ones, real polynomials. So we will approximate a function using orthogonal polynomials. So the simplest case, of course, is d equal to 1 dimensional. In this case, we can apply Grammar-Schmidt on 1x squared base. Then you get a base, and base called P0, P1, P2, where Pn is a polynomial of degree n. So then Pn, Pm just going to be simply, let's say our interval AB is simply integrate wx di equal to 0. So this is our general setting. So let me now look at the case and the simple case. On approximation, oops, what did I do? Okay, it's still sharing. I will need to go to full screen. Full screen again. Sorry. So I'm now looking at the Legendre polynomials. That's orthogonal on -1 to 1. The weight function is 1. So it's the simplest case, dx. And we know this orthogonal, this polynomial satisfies integral is 2 over 2n plus 1 delta n. Where this polynomial, you don't have the wrong Grammar-Schmidt. In this case, it's simple. You can write them down explicitly. It's just 1 over 2n to the n factorial dn dt n t squared minus 1 to the n. t squared minus 1 to the n, that's a polynomial degree 2n. You take nth order derivative, you get a polynomial degree n. Then normalized constant doesn't really matter. So for f in L2, the Fourier Legendre series is given by the sum you divide by this. This is the integral. Of course, this is just simply the norm. So, well, let pattern be the space of polynomial degree less than or equal to n. The error of best approximation by polynomial is defined by this. So you take infimum of all polynomial degree n. You look at f minus g, you take the p norm. So this is the error of the best polynomial approximation. So then what we wrote down before can be thinking about as the following. For p equal to 2, the Hilbert space, which we described in the first page, basically says that your error is equal to f minus Sn2, where Sn just the partial sum. You may ask your question, okay, L2, that's too much. How about LP? How about the uniform norm? Well, this all can be solved by using orthogonal polynomials. For p not equal to 2, let eta be a smooth cutoff function. A function looks like this. It's going to be 1 if eta t equal to 1 for 0 to 1. And then from 1 to 2, it's going to go decreasingly down and then become 0 afterwards. So now you define your Vn fx instead of partial sum, compare these two. You add a cutoff function. Nowadays, you could call them sampling. Well, if you take this cutoff function, you write down Vn then Vn is of degree 2n instead of n. And Vn actually is a polynomial of degree less than equal to, if f is polynomial degree less than equal to n, then Vn equal to f. So it's like the partial sum, except it's degree 2n and is recovered polynomial up to degree n. Importantly, then you can prove this always holds. So when f minus f is less than, is we call it almost or near best approximation polynomial. So with a price of a constant c, you essentially recover the best approximation for all p. So if r has order derivative, so it's a smooth function, then we know you can actually write down this quantity is error is cn to the negative r, and phi to the r power f to the derivative, where phi is square root of 1 minus x squared. So phi is actually less than 1. So you essentially have n to the negative r's power. So there's a trade-off between approximation order and smoothness. For every order of derivative, you increase your approximation by negative n. So negative, so n to the negative power. So you get this order, and this is the order you can get from smooth functions. So let's see what can be a problem. There is a potential problem with if you think about numerical solution of OD and PDEs, for example, by spectral method. I will later explain what the spectral method means. So we need to approximate both functions and its derivatives. You have differential equations, you need derivatives. So the question, is there a polynomial P such that for k up to r, fk minus Pn, the derivative, is less than that? Remember, for each derivative, we get a trade-off of n. There's a mistake. This should be f to the r's order derivative. So what you get is n to the negative r plus k. So you would expect something like this to hold. Our weaker form is this, n to the negative r plus k to r or p. So, well, for negative 1 to 1, such a polynomial Pn cannot come from the Fourier Legendre series. Indeed, for just p equal to 2, you would have fk minus Sn, the derivative of R2 norm is less than c times n to the negative r plus 2k minus half. You see the trouble compare these two. You have k minus half, too much. It's just simply not going to cut. And the order of magnitude in this estimate, this red number is sharp. You cannot improvement. So the question is this question wrong? Well, actually, the answer is yes, but the solution is given and understood only recently. So this was first observed by people working in numerical ODEs. They realized if your function has boundary value 0, you look at a equation, Sturm-Liouville type of equation. You have all the boundary condition being 0. Then you can somehow integrate by parts. Play some tricks. You actually hold, this thing actually holds, means that actually holds. So, but what about if the boundary value is not 0? Why does that work? So let's move a little bit to the Jacobi polynomials. So this is like last time I talked about the Legendre polynomial where W is 1. Now I have W are equal to this. 1 minus x alpha, 1 plus x beta. So the orthogonality is given by that. I'm not going to write down what Hn alpha beta is going to be. So the Fourier series called the Fourier Jacobi series is defined in exact the same way. And you can write down the partial sum also in exact the same way, just with the parameters alpha, beta, whereas 1 minus x with alpha, 1 plus x with beta. What we care is the case alpha equal to beta. So basically you have alpha is in x equal to 1, the beta is x equal to -1. So you have two endpoints, you have something additional. So you define the LP norm just like before, -1 to 1, and you integrate with this weight and the piece norm. So our previous result extends to the space with W alpha beta. For example, you can write down ENF LP equal to this arrow responding to secant negative R if you simply change this LP by W alpha beta. So everything holds. Well, if you let d over dx, you take derivative of this partial sum. It turns out this to be S minus K alpha plus K beta plus K partial KF. So your derivative somehow exchange with this operator. The derivative exchange inside, derivative goes here. But at the same time, you increase alpha beta by alpha plus K, beta plus K. For example, if alpha beta equal to 0, we are back to the original Legendre case. But then you take derivative, it becomes Jacobi. So in the formula from this exchanging, you can easily say that partial KF, the derivative of case order derivative, if you take derivative estimate, is become that. It looks almost right, except there's trouble. We have to change the weight function. So your case derivative, you have alpha plus R, beta, then become alpha plus R, where R is the largest one. In fact, this inequality, you can replace it by K, but that's not the point. The point is this holds only if you have different weight function. So now, if we could just choose R beta equal to -R, then we would solve my original question about the Legendre polynomials. If this is -R, then this would be 0. But W0 is simply 1. So that would solve my original Legendre polynomial problem. So this is where the trick is. However, W alpha beta, remember, is 1 minus x to alpha, 1 plus x to beta. It's not integrable if alpha and beta less than -1. And this is not well defined for alpha beta equal to 1, 2, . So we have a problem. Jacobi polynomial is not well defined. So the question is, can we find extension of Jacobi polynomial somehow? But more importantly, can we define a inner product to make them orthogonal? We have seen the orthogonal really is the key for this type of problem. Well, this is what we call orthogonality in Soppler space. So we define, instead of Well, we have singularities at -1 to 1. So why don't we simply define by taking integral over derivatives? Derivative t, g to t, dt, then I'm going to plot a bunch of endpoint. K from 0 to r minus 1, lambda k, derivative at -1, derivative at -1. -1 being one side, you could replace -1 by 1. That would be have the sort of the same type of thing. Now, I'm simply going, I don't need this actually. I don't need this. So just for alpha un, we define polynomial by this. You see, I'm simply taking integral of that. Well, from calculus, we know this really is the error term of the Taylor expansion type of thing. So you are simply doing this. Well, then these are in fact orthogonal polynomials with respect to this thing, where Pn is the Legendre polynomial. So you're simply taking antiderivative of the Legendre polynomial r times. And then, of course, for n less than r, then you have to replace it by this. Well, this is, in fact, your orthogonal base. And this was independent discovered in 2017. So here is what's going to happen. Well, this is the key to our answer. So we write down the Fourier expansion. We can still do the Fourier expansion as before. You can define the Fourier partial sum. Of course, everything here is negative r, where negative r being the orthogonal polynomial given not before. Then here is a solution. If f is in Sobolev space, which means you have p's norm, your r's order derivative, then for p equal to 2, you do have this is less than equal to that. That is the answer of our original question. Furthermore, for p between 1 and infinity, you can use the analog of weighted f, means by sampling this as a negative r of f. So in a sense, this works out well. So what's the moral of this? The moral is the following. If you approximate in the Sobolev space, use Sobolev orthogonality. So the original L2 case no longer work. But if you replace L2 by W2, then it should work. So let's now look at the more generally. So my goal is to look at orthogonal polynomial in several variables. So orthogonal polynomial in several variables is going to be much messier. So let omega be a domain in Rd with non-empty interior, such as like a ball. If you say not, well, the reason I add this, because when you think about orthogonal polynomial, you can also think about spherical harmonics. That's different because the dimension will be different. So let omega be a non-negative function on omega. We define the inner product as before. I just simply replace this by omega x to emphasize this somewhat little bit different. Let pi and d be the space of polynomial of degree n in d variables. So a polynomial p of degree n is called orthogonal. We still have this, but there's a but. It's for all polynomial of a degree n, where m less than n. But that really means I'm only asking is going to be orthogonal to polynomial of a lower degrees. In one-dimensional, that's all of it. In multi-dimensional, things are a little bit different because you have a many polynomial of same degree. Well, just like many, like this, xn, that's a degree n, that's also degree n, that's also degree n, that's also degree n. So let V and D be the space of orthogonal polynomial with degree equal to n. Then the dimension is that many. For example, if d equal to 2, you really have n plus 1 of them. So in one variable, we have only one. For d equal to 1, you have only one. But d equal to 2, you have n plus 1 of them. For example, if d equal to 2, our orthogonal base of V and 2 can be derived by the Grammar-Schmidt of xn, xn and y, x1 and yn. Then you get an orthogonal base. So you have to do this for every degree you want to generate a whole base. So let's look at a little bit more. So a base of V and D, we can index as pkn, where k is a multi-index. So k is k1, k2, kd, and where k equal to n means you sum all the index equal to n. So it's the total degree equal to n. So for d equal to 2, for example, this side, k equal to n side, is 0n, 1n, nn. So this is just your xn minus 1 y, and dot 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 to y to the power of n. So in this case, because of V and D are not unique, not necessarily orthogonal. So basis of this thing may not be unique. You can have many, many different bases. And the order of monomials matter. How you take Grammar-Schmidt, what order you take, you will get different base. Example, on a unit disk, B2 is x squared plus y squared less than equal to 1. With the classical weight is 1 minus x squared minus y squared to the mu bigger than equal to 1. So again, the weight function going to vanishing or have singularity on the boundary of the disk. Well, you have two sets of orthogonal polynomials. One side, I'm going to use Geigenbaugh polynomials, C and lambda. So I'm talking about all this Jacobis. So there's Geigenbaugh. So what is Geigenbaugh? Well, Geigenbaugh is a special case of Jacobi polynomials. It simply means Cn, Pn, lambda minus half t. The constant looks ugly, but this basically customized, normalized. Well, it started as this: 1 minus 2t r plus r squared to lambda, write down an infinite sum. Very neat, very nice. The Geigenbaugh polynomial sometimes called ultra-spherical polynomials. If you do mathematical physics, you probably recognize this appears there. For lambda equal to d minus 2 over 2, then that's associated with solution of Laplace equation. So if you take x and y as just xy, then this is your base. You take the Geigenbaugh polynomial to k plus mu plus 1, where mu is this thing, and 1 minus x k over 2 times this. So you can, it's a little bit, hey, there's a square root of that. Yeah, there's of that. So you can check it actually is a polynomial of degree n, and they are actually orthogonal. So that's one base. But I said that there are many different bases. For example, on a disk, it's natural to take a polar coordinates. So if you simply take a polar coordinates, you take Jacobi polynomial, takes r, you take that. Well, you can verify this is in fact an orthogonal base. Of course, it's an orthogonal base, but it doesn't look like a polynomial. There are x and y. Well, you can actually rewrite it backwards to make it into a polynomial degree n in x and y. So they really have different bases. Well, we should realize orthogonal polynomial with index and pkn. So this is orthogonal base. Well, the fully orthogonal series you can define as before. Very much as before, except your sum getting uglier. You get n from 0 to infinity, sum of all k. Remember, k is a multi-index. So this really is a mess, right? You have to be careful about how many, well, if it's d variable, you have d minus 1 layer just over this. That's too much. Well, the projection operator, you should take our two function to this orthogonal base, and n-dimensional partial sum. These are defined by that. So first, you take the sum over inside, over this, inside. This is the orthogonal projection. The partial sum simply means you add the projection up. So we still want the partial sum to depend on only one index, n. So the fully orthogonal series can be written as f equal to sum of that. So therefore, your function f can be written as this. Snf would be a good approximation to f. That's the partial sum. For studying fully orthogonal series, what we need is this kernel. You see, I said that base is a mess. And very few people want to work with the base. It's just too much. It's difficult to handle, and it's almost no way to handle it. But all we need is this kernel. So which is this is like the Dirichlet kernel in the Fourier series. Well, this kernel, it may have a closed form independent of basis. So the beautiful part of this is, like in the classical Fourier series, if you write down the Fourier series, the sine and the cosine, it's a mess. But if you write down Dirichlet kernel, it's much, much easier to handle. So this would be the equivalent of Dirichlet kernel. So let's say, take the classical case of orthogonal polynomial on the ball. This will be my primary example of this. If you take this case, 1 minus x squared to the mu bigger than -1. We wrote down the d-dimensional degree 2 case before. The projection operator satisfies this. You write down the kernel, then you integrate. So what does kernel means? Kernel is the one I defined before as a sum of a product of orthogonal polynomials. Well, reproducing kernel in this case took a very simple form. It's simply this. You take a lambda equal to mu plus d over 2. Then you take, this is constant. Then you integrate Gangler polynomial, a one-dimensional integral. Sorry, this is dt, not dx. You take one-dimensional integral, but your z is a little bit complicated. It's x dot y is the inner product of Euclidean inner product, not the orthogonal. Then plus square root of another mistake is treating x the norm. Sorry, x norm square. So you write down this thing, you simply integrate it. Most important part, this is a one-dimensional thing. So your whole messy sum come out to be a very, very simple form. And this is the key for our basically study for orthogonal series on the ball. And we also know this orthogonal polynomial are eigenfunctions of a differential operator. So you take a second order differential operator, you apply for any polynomial in this, you get an eigenvalue. So this is very nice and very simple, which says orthogonal polynomial on the ball are very much structured. It has many interesting properties. So let's now go back to approximation on the ball. So some result on approximation on the ball, on the B1, which is -1 to 1, one-dimensional ball, can be extended to BD. So for F in LP, BD omega mu, I'm not thinking about the mu equal to just for any mu. You can define this again. You can define the error of best approximation and the infimum of F minus G, where G is any polynomial degree n. The same quantity as we define in one variable. For F not equal in L2, we have F equal to the sum. You define the partial sum, define this operator, where this is again a cutoff function as before. Then we still have this thing. The partial sum gives you the least square approximation for L2 norm, 2, and this is the LP norm. So you also have, sorry, too quick, you also have this. So if F has all the rth order derivatives, then you still have this thing holds. So you forget about the norm, you still have n to the negative r. So everything should work just like in one-dimensional. Okay, let's consider now Sobolev space. So I'm interested in Sobolev space. I want all partial derivative rth order is LP. Well, for p between 1 and infinity, and then continue uniform norm with p equal to infinity. Its norm is defined simply by that. There should be p here. So although this, I now consider mu equal to 0. So that's simplified to only mu equal to 0. So that SNBD without W mu, I consider mu to 0. So this partial sum is best L2 approximation for F in W2. However, if you look at the norm, it's not going to work. Like in one-dimensional case, if you look at the norm, your norm is Cn negative R plus 2s minus half. Well, compared to what we need, normally is 2R plus S. Again, you have this trouble. S minus half mysteriously appeared here. This estimate is sharp. And this was proved by Leonardo in 2017. So this estimate is sharp. So like the one variable, we cannot do it anymore. You have to think about something else. What we hope to find is another polynomial P of degree less than n such that this holds. So you look at the subderivative derivative of order S, you want the bounded for function norm, you want negative R plus S. So you still need this thing. But what we have from L2 is that. So clearly now we should switch to subderivative norm. But let me now explain the problem coming from PDE. So how does the spectral method work? I think this is a good point to start a little bit detour to think about spectral method. So let me think about the simplest case. So this is the Poisson equation. So consider the Dirichlet problem. So Laplace equation equal to U equal to F in the ball. With the boundary, you have a function G. Boundary is the sphere. Think about D equal to 2, then boundary is just a circle. So, well, how do you solve something like this? We often write it in a integral, a variation form. So what I mean is, I'm running multiply by a v to this thing, I'm integrating by parts. So then you can write down this, combine both of them into one equation. It says the gradient of u dot gradient of f v, you integrate this thing on ball, and then you write down f times v you integrate on ball, and then g times v on the boundary. So this is the variation form of the equation. On the right-hand side of the boundary, there are the f times v and g times v. This is integral on the ball, this is integral on the surface. So this is it. So, well, numerical solution, what does that mean? The spectral method looks for an approximation solution Un. It's not a infinite series, but a partial sum. The sum, you sum over all polynomial, a sequence of polynomial. It's going to be an orthogonal polynomial. But let's first assume this is only a base of all polynomial up to n. And right now, n from 0 to capital N, k equal to n, sum of all. It's a polynomial degree n. So how am I going to do this? I'm still going to say, hey, I don't know what this u is. I'm going to choose u capital N. Should be capital N here. U capital N equal to that. I'm simply dump this u capital N into this. So what's going to happen? I'm going to say I should replace by u to n into this. I'm asking for what v. I'm going to choose my v as some special form. So I'm going to choose v so that our AKN means these coefficients are determined by a linear system of equations. How do I do that? I'm going to choose v equal to qin for I up to n less than that. Then my AKN is going to satisfy this equation. You see, this is the linear system of what equation. It simply means that. Of course, the matrix become, well, if you choose just QKN randomly, it's going to be messy. But if you choose this as this equal to 0, I not equal to k, this become diagonal. So that would be very, very simple. So that's where the orthogonal polynomial comes in. You want to choose f and g is equal to make this equal to 0. Of course, it's not exactly 0. You still have to add something because otherwise you don't have a complete inner product. So this suggests that we consider the inner product as this, fg equal to that. So you see I'm switching inner product with a gradient. Well, the error estimate of this, for the error estimate, we expect something for this to hold in this Poisson form. We need only first order derivative and function value. Combined, it give you in the Sobolev form is 1 to the 2 less than equal 1 to the r. So this is what we need. So let's see how this is going to work. So think about the Sobolev alternatives. So I'm going to use what gradient. So what I'm going to do, I'm going to simply define definition. Laplace to the m power is simply nabla to the 2m. But if it's 2m plus 1, then would be saying nabla, then there's the Laplacian to the m's power. So of course, then we can define inner product just as like that. So if d equal to, well, if s is even, then this becomes simply a Laplace to the m's power. If it's odd, you'd have to take a inner product of the two. So now I'm adding Laplace, only Laplace form on the surface and up to S2 minus half. So this is, you can prove this is a well-defined inner product, not L2, but W2, sorry. Now V and D denote the space of OP with respect to this. So I'm adding this red omega to negative s to emphasize this is actually orthogonal polynomial with respect to this strange Sobolev inner product. So I'm not going to bore you with the details of how to construct the base. I'm just going to say, then we can construct orthogonal base, can be explicitly constructed in terms of Jacobi polynomial and spherical harmonics. Where Jacobi polynomial, you have a negative s, but this you can verify, they can be defined properly. Then this orthogonal polynomial of the form of this, where this is the Jacobi polynomial and y is simply the spherical harmonics. So you define this thing, and what we know is the following. You can define the orthogonal projections just as before. You simply remove everything rather than before by this Q. You put the inner product by this thing. Then the projection is the usual, that Pn0 be the classical usual projection on the ball. Then the amazing part is your Laplace operator exchange with this new to inside. It's like you from the one dimension you have Sobolev, you take derivative, then it becomes the Ranger. Well, this is the same thing. You take negative s, you take derivative, you back to classical orthogonal polynomials. So this is the key. So this allows us to do the following. You take the partial sum, you take that. Then you still have, so like the partial sum of my Sobolev orthogonal projection. Then I take a sampling, just like in one-dimensional case. Now, if f is in Sobolev WRP, then you do have this holds. So that means you do have recover everything we said before of what we need. You can say a little bit more than that. Say a little bit more in the sense, well, you can say that for the case order derivative, you have like r plus k. But for our purpose, for estimate for the PDE, this should be enough. It's just about enough to have this thing. While the proof is a little bit complicated, you need some heavy machinery from PDE and boundary value problems. But let's see. So this is what we can do on a ball. At this point, you realize a ball is very special. It has a closed form for its reproducing kernel. It has PDEs. It's a very well, structured thing. You probably should wondering, can this be held for any other domain? Well, unfortunately, this is a multi-dimensional thing. If the domain is very general, there's usually very little tools you can use. So we usually want to have structures. So what kind of structure can hold? Well, for the orthogonal polynomial on the other domains, well, the most important for the ball is probably the following two properties. A closed form for the kernel, for the reproducing kernel of Pn, and differential operator such as du equals negative lambda nu. So anything else to hold for this thing? There's quite a few. For example, unit sphere. Well, this is the classical formula for the addition formula. Lambda is d minus 2 over 2. You can replace by lambda kappa if you have this, have the sphere with weight. So for this, but you realize your reproducing kernel is getting much more complicated. But no matter how complicated it is, this is still a one-dimensional structure. Means you have Jacobi polynomial, one variable, you have a more complicated structure. But other than that, all should be fine. Anything else? Yes, you can have a weighted ball, you have a simplex, and you have some product domains. Well, recently I started work on this thing for other quadratic surfaces. Instead of sphere and balls, you can have, for example, cones and bounded by quadratic surfaces. So something like this, the cone, this is the hyperbolic surface. So you can have those things. So now you have similar things. For example, on the conic surface, the first one, you simply write down d mat plus 1 x in the d variable t is 0 to 1. In this case, you do have a complete structure. You have a PDE, you have integrals. An integral in this case is taken of this form. You notice this is looks pretty bad. It's a two-dimensional integral, but it's not as bad as the one on the sphere. So this is actually new. This was really discovered last year. So anything else, like PDs or even the approximation order for the partial sums, I don't know it yet. So I think with that, and my time is up. So yeah, thank you.
Okay, many thanks, many thanks, Yuan. So maybe we can. Is there anybody with has anyone questions? Are there any questions? Okay, maybe I can. I would like to ask something. If is so you say this is you can now do this is rather new. This thing you can now do hyperboloid surfaces and cones.
Yes.
And what? How did you get to that kind of domain?
On the cone. Yeah, actually, a few years ago, I started thinking about, well, we did a lot of things on the balls and on the spheres. And then I started asking myself what other orthogonal structures are there in. So the natural thing would be, how about simply replace sphere by something else? So it's a quadratic surface. So then I started looking on the quadratic surface to see what can I do. And this is what comes out.
Okay.
So it works for the cones, works for the hyperbolic surface, but for parabolic surface, it only works partially, not completely working. And for the, well, if you don't have this hyperbolic surface of a two shade, but a one shade, means you take the hyperbolic curve and you simply rotate it in the other way, not in the way around, but in the other way, it does not work. So there are some mysterious things about this.
Yeah.
And of course, this is new, so there should be a lot of things can be done over this, I think.
Yeah. So you still you say you need to know the eigenvalue problem. Yeah.
Right.
So you know in for example in the cone, which is an unbounded. This is an unbounded domain,
Yes.
isn't it?
Yes. That's a very good question because the example I gave, I cut off the cone to finite. So this is like the Jacobi
All
polynomials.
right.
If you take the infinite dimensional, not infinite dimensional, infinite cone, it becomes Laguerre. And in that case, you still have um, differential equation. And that then you can write down the the reproducing kernel, the closed form formula. But the reproducing kernel is no longer the kernel is no longer positive.
All
So it's
right.
involved the Basel function is getting more complicated.
All right.
But it's still interesting. There should be a lot of things to this. There's one interesting thing is the Laguerre expansion has a strange connections with the solution of wave equation. And I don't really understand why. But if you write down the wave equation, you can actually find explicit solutions for the wave equation on the cone.
All right. All right. Thank you. Has anyone? Is there anybody else with any question or comment? Well, well,
I have
if
a
not,
question. I
okay,
have a question.
okay,
Yeah.
Yeah.
please.
Sorry. But first, many thanks for your talk. It's really a pleasure to have a person of your caliber here in our meetings here. I just have one question. Is there any interest in considering other operators, not only derivatives, for example, Dunkel operators or any
Yes.
other stuff?
Yes. Yes. Definitely. Basically, on the sphere on the ball, you can think about basically all the structures in the harmonic analysis actually works over here. You can think about Schrodinger operators, or you can think about Kate equation. So you can basically consider many different ones, and really this is a tool. So if you look for the Fourier Fourier side on the
Mhm.
on the Rn, you usually look at the basically Fourier transform or Hermite expansions. On the ball, on the sphere, the tool really is the spherical harmonic and orthogonal polynomials. I think the same should hold for the cone and for the other things. So this is essentially a basic tool. So it's just a matter of how we're going to use these tools.
Okay, many thanks. I was asking about is there any interest in considering, for example, a Dunkel analog of the Sobolev inner product, for example?
Yes, actually, on the Donko side, it's getting more difficult. The part of the reason you have to replace partial derivative by the Donko derivative. So, but something we should be able to do something on that.
Okay, many thanks.
Yeah.
Okay, all right. If there are no further questions,
Okay, thank you.
remember this is being recorded, so it will be uploaded eventually. And so we thank our speaker. Many thanks, Yuan. We have to clap from the screen, but
Yeah.
many thanks.
Yeah. Thank you.
Yeah, many thanks, Professor.